Okay, so I'll use 130. Okay, so I'm going to continue pretty much from where I left off. Yeah. So I was talking about coherent algebras, and got as far as proving that every coherent algebra has got a basis of 0-1 matrices, and I want to talk a bit more about that. So we can call a 0-1 matrix in the coherent algebra minimal if you can't write it as a sum of two non-zero 0-1 matrices. So you can't split it into two parts, both of which parts must be in the coherent algebra. And the point about that is simply that once you have this concept of minimality, you can say that the canonical basis is formed by the minimal 0-1 matrices in the algebra. And since these matrices are 0-1, and since they don't overlap, they're obviously linearly dependent. So you get a basis. Now, and as I said, you can always you can write each basis as a long skinny vector, and then you can order them lexicograpically. So there's if someone gives you the algebra, you can get the basis, and everybody who works them out and uses the same ordering will get the same basis. So it has a unique basis. Okay. Now, which we usually call a canonical basis. Now, the couple of special cases, if the identity matrix is a 0-1 matrix, and so it's either minimal, in which case it's in the canonical basis, or it's a sum of 0-1 matrices. Now, if it's a sum of 0-1 matrices, those 0-1 matrices must be diagonal as well. Okay, and so in that case, you've got a partition of your vertices, and the cells of that partition are sometimes called fibers of the coherent algebra. If the identity matrix is minimal, so you can't split it up, then the jargon is that the coherent algebra is homogeneous. Okay, and a couple of things I'm going to leave as exercises. They're not that a commutative coherent algebra is homogeneous. Okay, converse isn't necessarily true. I'll give you an example in a moment. And if the coherent algebra is homogeneous, all the matrices in C have constant row sum. Now, if I is not minimal, then you can write it as sum of diagonal 0-1 matrices, and you see that the row sums aren't constant. So one direction is completely trivial. Well, it's very easy anyway. So we have this idea of concept of homogeneous coherent configurations. Basically, coherent configurations aren't easy to work with, and so anything you can do is to make them better behave is worth having. Now, what I want to do now is discuss some sense that the most obvious class of coherent configurations we get from permutation groups. Now, if we have a permutation group, the set of matrices that commute with it is an algebra. If A and B commute with a permutation, then so does their product. Okay, and so you can see very quickly that the commune of G, we also saw that Scher closed, so it's going to be a coherent algebra. In fact, it's homogeneous if the graph is transitive. So in this case, what I was calling the fibers would have to be the orbits of the group. Okay, and so if the identity matrix is not minimal, then the group has got at least two non-empty orbits on the group. So in the permutation group case, homogeneity corresponds to being transitive. Okay. Now, if G is transitive, then at the start of the course, some point I was talking briefly about orbitals. Now I'm going to expect you to remember the claim is in that case the orbitals are the basis for the commutator. So the orbitals are the orbits on ordered pairs or arcs of ordered pairs of adjacent vertices. Okay, and so if the graph is transitive, things break down. You split things to orbitals. One of the orbitals is the identity. The other orbitals are not. They're adjacency matrices of directed graphs, and in general they don't commute. Okay, so we would have a homogeneous coherent algebra. It wouldn't be commutative. Okay, if the coherent algebra is commutative, then it's equivalent to what's usually called what we normally call an association scheme. And I did say I wouldn't be talking about those, so I guess technically I'm just going to say I'm going to talk about community coherent algebras occasionally. So that's just jargon. So the community case is special for reasons which will become apparent as we go on today. So we have coherent algebras, and so we have in particular we have homogeneous coherent algebras, and that's going to be a case of most interest to us. Now, more jargon. The elements of the canonical basis of coherent algebra, or yeah, it should be the set of elements or something. I'll just make that grammatical just while I'm here. So the set of elements of canonical basis is known as a coherent configuration. So you've got essentially what this is giving us a second way of looking at structure. On the one hand, we're looking at the entire algebra and talking about that. On the other hand, we're just going to focus on the elements in the canonical basis. Now, I find it generally easier to work with the algebra. And I think in the long run, it would be easy for anybody. It's not quite clear in the short term. The coherent configuration. So coherent configuration, this is you take the basis matrices. Okay, there's 0, 1 matrices. And so they're adjacency matrices of directed graphs. Okay, and I've listed some of the properties here. I will go down to here. So they're 0, 1 matrices. The distinct matrices, have show product 0. The set of matrices is closed under transpose. So if BI is one of your basis matrices, then BI transpose is also there. Okay. Secondly, these matrices sum to the all ones matrix. The identity is the sum of elements in the standard basis. Okay. And there are scalars, beta jk, such that BI times Bj is a linear combination of basis elements with coefficients pi jk. Now these scalars will actually be integers for what that's. Because the product BI Bj is a 0, 1 matrix, and now you're going to write it as a linear combination. So the product BI Bj is an integer matrix with non-negative entries, and so now you're going to write it as a integer linear combination of 0, 1 matrices, and so you get that. Okay, so you have all those properties. Okay, and if you add associativity to it, so if you add commutativity to it, then you've got an association scheme. So we have those. So in fact, when these things were originally introduced by Higman, they started with the coherent configuration and then worked with the algebra. Life is generally easier if you just say you've got a coherent algebra, an algebra of matrices that's closed on the Schur product. Okay, and you can see these axioms are implying that these guys, the canonical basis generates matrix algebra. I mean, it's telling you the product rule. So BI times Bj is linear combination Bk. So you've got a matrix algebra with the BI as a basis, and it's Schur closed. Okay. Any questions at this point? Right. So okay. So that set of 0 matrices is called a coherent configuration, and you'll see reference to that in the literature. For what we're doing, it's not surprising in a certain sense. We don't need to mention the configuration. We can always just make do with the algebra. Okay. So now one difficulty with coherent algebras is there's certainly no textbook which gives a nice discussion of coherent algebras. One reason is that it's not a simple topic, and the actual places where you need it are reasonably limited. So you could focus on the community case, and there's lots on that, but there's not a big literature. And there's a fair bit of confusion I find between when it comes to discussion about isomorphisms of coherent algebras. Okay, and so I'm going to go through this carefully, which is always tedious, but we'll do it. So the first thing to notice is an algebra is a ring. So it's basically a ring with a field sitting in a center. It's slightly more complicated than that, but so basically a ring. And so it's simultaneously vector space for a field that sits in the center of the ring, but let's not worry about that. So an algebra is a ring. And so isomorphisms of algebras are ring homomorphisms. Homomorphisms of algebras, I should say, I guess. Let's just for fun of it. Some number of ends and O's there, but that's probably approximately right. So, so an algebra is a ring, and so a homomorphism algebra is a ring homomorphism. Now, you could be in some situation where you want to use something different, but then you'd need to apply a lot of explanation, and it wouldn't be clear what was going to happen. So, nonetheless, an algebra is a ring, and so any homomorphism is a ring homomorphism. So, the image of x times y is the image of x times image times y, and similarly, the image of x plus the image of x plus y is the image of x plus the image of y. So that's the usual obvious things. Now, since our algebra is vector spaces, we will always assume that our homomorphisms are linear maps. Okay, so we've got this vector space structure, and so your maps need to preserve that, that nicely, that structure. And the way that a map interacts nicely with vector spaces is it turns into a linear map. Okay, so it's still a ring homomorphism, blah, 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 but it's actually given by a linear map because we've got this vector space structure there. And if you call something an algebra, you expect your maps to preserve the algebra structure, and that means it should preserve the additive structure, or the additive structure. Now, the problem with trying to define isomorphisms, well, I think I just go through it. So an isomorphism from a coherent algebra to a C to a coherent algebra D is going to be a linear map. I'm calling it beta. Yeah, so beta is a ring homomorphism. And we also, since we didn't get information, we've got the shear product to worry about. So we're going to insist that you preserve the shear product. Okay, that's obvious enough. Okay, so it's a linear map, it's a ring homomorphism, and it preserves the shear product. Now, that's well and good. Everybody's going to assume the linear map is going to send a matrix M to A inverse MA for some matrix A. And that's often what happens, but it's not the only possibility. Okay, actually, it may be better if I do this explicitly. So suppose script M, is an algebra of matrices. And my question is, what are the linear maps from M to itself? Now, if you want them to be invertible, so typical would be something like M going to this. So I'm going to call that a similarity. Now, the point about similarities is that they're going to be isomorphisms. They're injective. Okay. And I'm not really assuming that right at this point. More generally, you're going to map M to A, M, B. That's a linear map. Oh, that's okay. That's not too surprising, but well, there's no reason to stop at that. In fact, in this case, it's generally better to transpose the B, but I won't fuss for that this time. It doesn't matter. So this is a linear map. And in fact, it's not too hard just by a dimension argument to prove that all linear maps from M to itself can be given this form. Okay, so we do have a description of the linear maps from M to itself. Okay, now you might have some extra conditions if we want this to be a ring homomorphism. Then there's extra restrictions on what happens on the choice of A and B. But this is just, I'm just looking at the general case. What are the linear maps from M to M? Okay, now you can, as I said, you can use a dimension argument to show this will give you everything. It's not, I guess it's not completely obvious that you can stop at a finite number of terms, but you'd be surprised if it didn't. So okay, that's all right. Now, but my next question is, I want it to be invertible. And so, well, the real point is, okay, you've got this source, of you've got these maps, and so so these are the linear maps from a matrix algebra to itself, and then if I want to have an isomorphism coherent algebras, I'm going to attach extra conditions. But my point is, you're not going to be just writing down matrix similarity in general. Now, nobody really wants to work with this, and so you'd like to have a theorem that tells you that if you had an invertible linear map from the algebra to itself, with a similarity. So you'd like to say, now there's already a problem here. If I do a similarity, there's two cases. I might choose A to be in my algebra itself. That would, and so that's legal. Or I might choose just to be a matrix the right size that works. So I've got two choices there. Okay. You can show on, the basic theorem is there's a Skolem theorem. Which tells you that if you're dealing with a so-called central simple algebra, then the invertible linear maps are just conjugation by elements of the algebra. And so the full matrix, so if you look at the full matrix algebra, the invertible linear maps of that to itself are just similarities. If you're looking at subalgebras of that, the invertible linear maps taking your subalgebra to itself need not be similarities. Now, so there's two ways of doing this. One is you try to make sure that you're dealing with something which is a central simple algebra, or whatever that is. And the other possibility is you're just going to say, well, I'm just going to stick to, I'm not going to look for arbitrary isomorphisms. I'm going to look for similarities. And in practice, that seems to work. So nobody tries too hard. Okay, and so if you're working with current algebras, it's perfectly natural to say, oh, I view isomorphism as similarity. Okay, the point of all of this, I'm warning you, is that the actual definition of isomorphism, if you really have to get down to details, it's more complicated. Okay, and so if you choose to work with similarity, that's fine. And so my point is just you have to recognize that you've made a choice. Okay, and it's not impossible one day you might find yourself in a situation where you have an isomorphism which is not a similarity, but it's not going to happen to us. Okay, so isomorphisms are a little bit more complicated than you think. We would prefer, we've got a definition here that covers what we need. And okay, that's the general definition. And as I said, we're going to have, so I want to give that point is we have this special case of similarities. So we have similarities, and that's what we normally want to work with. Now, actually, that's not enough. The point is that when we look at our canonical basis, it consists of 0-1 matrices. And if we're homogeneous, these 0 matrices are the identity and a bunch of directed graphs, each of which is going to have constant row sum. So we look, nice. So we have a number of regular directed graphs. Okay, and we all know graph isomorphism, we want permutation matrices P such that P matrix P transpose is equal to P first matrix M transpose is equal to the second matrix. Okay, and so then we have, so that's a form of similarity because P transpose is P inverse. Okay, but it's permutation similarity. Okay, and so so the two cases you're normally dealing with are either similarity or what I'm just calling at the moment permutation similarity. Every person who deals with the subject gets to make up their own names for them. And they're often called things like weak and strong isomorphisms. And I can never keep those sort of terms straight. But you just have to be aware. Okay, so you can, from my point of view, I'm either going to deal with a similarity, which I'm used to, or they're going to be permutation equivalent. And as I said, in some places, these will be called weak and strong isomorphisms, but I forget which is which. Do you have a theory, Ada? No. Okay. That should be a scorn. Now, if you look at my list of conditions for the homomorphism algebras, I said you got to respect the Schur product. I didn't say anything about what happens to the or once matrix. Now, the important thing is the ring homomorphism, the convention that all algebraics use is a ring has an identity, and the ring homomorphisms must preserve the identity, and a subring must contain the identity. In some parts of analysis, they're working with rings and they don't insist on the identity being there for reasons which are fine. But we insist there be an identity. And so I've got a coherent algebra, and I've got this Schur product structure there. And so normally you want to make sure that the homomorphisms preserve the Schur product structure, so they should map J to J. And so what I've got here is proof that we don't need any extra axioms to take care of that. We get that for free. Okay. And so the point is, if you've got an isomorphism in algebras or homomorphism, you certainly get. We certainly have. This is true because J is equal to J, and then because beta commutes with J, we see that beta J is equal to the square of itself, and so that means that beta J is a 0, 1 matrix. And then you calculate, well, if the matrices are in by n, then n times beta J is beta times nj, which is beta times J squared, which is beta J squared. And so beta J is a 0, 1 matrix, and beta J squared is equal to n times beta J, so each row of bj sums to n. Okay. So I didn't really need isomorphism in this. All I've assumed is that we might as well actually fix it. All I need is homomorphism. Now it turns out that you don't get any. There's no real need to think about homomorphisms. The only morphisms you're going to be dealing with are going to be isomorphisms. I didn't stop to try and prove that, but in any case, the J. So if you have a homomorphism between two coherent algebras C and D, then the J in the first one gets mapped to the J in the second one, and the size of those matrices are the same. So the dimension is not dropping. Okay, we don't need all that, so I'm not going to go into it. So the point is, we get a certain amount of stuff coming for free, and so we don't need to fuss about it more than that. And so now this is summing up what I was saying before. There are two special kinds of isomorphisms, similarity and permutation equivalence. Okay. And in practice, these are the ones that people work with. Okay. My rambling on earlier was to say that that this is not a complete list. It seems to be enough for what happens in practice, so we stop there. And now the key comment here is that whatever version of isomorphism we use, the isomorphism maps the canonical basis of C to the canonical basis of D. That's because you can show it maps 0, 1 matrices to 0, 1 matrices, and it maps Schur orthogonal matrices to Schur orthogonal bases, so it maps the basis of one to the basis of the other. Okay, so it's if you think of the basis as being a bunch of directed graphs, the worst the isomorphism can do is permute those around a bit. Okay. In fact, so I was defining my homomorphism between coherent algebras to be a map that commutes with the Schur product. There's an alternative way of doing it, dealing with it, and that's to say that it's an isomorphism coherent algebras is an algebra homomorphism that maps the first basis of the first algebra to the basis of the second algebra. Forget about the Schur product, because the point is, if you're given the basis, you know what the Schur product equivalent for the basis is. It's a different of 0. And so if you're given the basis, you can reconstruct this. You can write down the Schur product for any two matrices. You write each matrix as any combination things to the basis, and then you multiply things together and expand the usual way. So you could alternatively just say the map is an algebra homomorphism that maps the basis of one to the basis of the other. Now, there's nothing wrong with doing things that way. Sometimes there are even advantages, but it's a second approach. And one of the points here is that the basis is quite important. If you've got the 0-1 basis, preserving the 0-1 basis is enough to preserve the structure. Okay, so but that's enough about recondite details. Getting back to examples, if X and Y are strongly regular graphs of the same parameters, their coherent algebras are similar. I mean, the adjacency matrices are similar, okay, and that similarity maps is going to map J to itself and the identity of itself. And so the coherent algebras are similar in the sense I made above if you get dealing with strongly regular graphs of the same parameters. So there's something like 25 Latin square graphs of the board of on 25 vertices, and so any two of those have the same coherent algebra. Okay, so you can have lots of these things, and of course it can only get more complicated if the algebra is not required to be commutative. For the strongly regular graphs, the coherent algebra is commutative. It's a 0-1 basis. The 0-1 basis is the 0-1 basis is going to be I, the adjacency, and J minus I minus A. That's the canonical basis for a strongly regular graph. Okay, and so yes, it satisfies all the conditions that I wrote down earlier. So the strongly regular graphs, our life is fairly simple. Okay, now the reason that I'm concerned with coherent algebras is because they turn up in connection to quantum permutations. Now, I can summarize what's happening fairly briefly. If we have a set of permutation matrices, then the commutative is Schur closed. So I can say that the commutative of a set of permutation matrices is a coherent algebra, which is an interesting and useful fact. What we're going to see is that we're going to define quantum permutations, and then we're going to argue that the commutative of a set of quantum permutations is also a coherent algebra. Now, there's a few wiggle words creeping into that, which I haven't supplied yet. But so as you go from permutations to quantum permutations, you still get coherent algebras. Okay. And so this enables you to get some understanding of what's going on in a quantum case based on what you've already seen in the standard case. So, and for me, it's quite striking that as you go from permutations to quantum permutations, you still retain this coherent algebra structure. So the quantum automorphism of the graph, it's a quantum permutation matrix. So it's a matrix of projections, and each row and each column sums to the identity. Okay, that implies that the matrices in each row and each column commute for what that's worth. Now, the condition that to be a quantum permutation is not a quantum automorphism is simply that it commutes. Now, the wrinkle is, and the wiggle words I was just referring to, we're not interested. It doesn't commute just with A, it commutes with this. So you're taking your matrix, adjacency matrix A, and you replace each entry by the entry times the D by D identity matrix. Okay, so it doesn't change things much. You know, I know it depends on your point of view, but so anyway, in any case, that's the definition, and there's no arguing about definitions. This is the definition we're using. Now, you could similarly define quantum isomorphism just by putting AX tends to Y on one side and AY tends to V on the other side. Okay, so so the difference, as I said, as we go from permutation matrices, we're looking for permutation matrices to commute with A. So the quantum case, we're looking for the permutation matrices or the quantum permutations of index D that commute with AX times ID. Now you can encode this in such a way. If I set this up in the right framework, I can make this look like just the script P times AX is equal to script A times P. But I'll be reinterpreting some of my terms. But it's easier just to write that explicitly. So we'll leave it at that. So if these happen, this definition of quantum isomorphism. Now, I should admit first up, it's not immediately clear from what I said that a quantum isomorphism is a quantum homomorphism. And that will come out, some of that will come out of the exercises. But it turns out not to matter to us, so we're right now. So the point is that this is our definition of a quantum automorphism, and this is the definition of a quantum isomorphism, and that's what we'll be working with. So there are a few details which you need to think about at some point, but we don't need to think about now. The other point is these things, quantum permutation matrices are frequently referred to as magic unitaries. I'm trying to break Maria if I haven't, but there are various terms at the start, but it's fairly clear that calling them quantum permutations is the right thing to do. And they are analogous to classical permutations, and you have this connection between the community algebras and stuff. So that, and you know, if you say quantum permutation, that gives you some idea of what's going on. If I say, I guess you can say that quantum is a synonym for magic in the real world, but that's another story. But anyway, so you see references to magic unitaries, and there are also things called quantum Latin squares, which are a special case of quantum permutations. We'll come back to that, perhaps. A couple of things will be sort of straightforward exercises, and that's where you see them. A quantum permutation, if you think of it as index D, it gives you an ND by ND matrix, and that matrix is unitary. Okay, so that's another argument that is a natural enough concept. So it's a unitary matrix. The other comment here is that the quantum permutations fix J tensor ID, and so I should also say, I just want to say the converse to the first claim is also true, that if you have an ND by ND unitary matrix and the entries are projections of order D by, so with in this block projections of D by D, then it's a quantum permutation. So the well, the fact that the row sums and column sums equal ID gets forced by the fact that it's unitary. Okay. Now, if we've got quantum permutations, then we can define their coproduct and their direct sum, and so the product and direct sum of quantum permutations is a quantum permutation. And if P and Q commute with AX, then the coproduct and the direct sum also commute with it. Okay, so things work as expected there. Now, notice that if you're dealing with classical permutations, and the coproduct is just the ordinary matrix product. So no issues there. The direct sum, well, I don't think anybody's ever bothered with it. And so the direct sum of quantum permutations, well, it would be a quantum permutation according to our definition. Okay, it's not considered much. You don't need a lot, but the point is you get a quantum permutation. Now it turns out those quantum permutations tend not to be, well, the issue is the physicists want to distinguish between things that are really quantum and things that aren't. Okay, and so the key test which I should have written down here somewhere, is that the question is, do the entries of this quantum permutation commute? Do every two of them commute? If they do, well, I'll come back to it in a second, then you can say you're dealing with the classical situation. If they don't commute, you'll have something that's quantum. Now, this is unfortunate because sometimes I'll use the term quantum permutation and with the idea that this excludes classical permutations. Okay. Now, the point about the direct sum of classical permutations, the entries always commute. So you're not going to get anything sort of interesting from the quantum mechanics point of view. Actually, if you're but you get some. So the direct sum of permutation is not something that permutation theorists have ever looked at, as far as I know. Okay, but it is there, but it doesn't give you anything quantum because it doesn't give you a quantum permutation where the entries don't all commute. Now, I mentioned this once before, but if the entries do all commute, well, they're projections, so they're normal matrices. And if you've got a collection of commuting normal matrices, then you could change basis and make them all diagonal. Now, if you diagonalize a projection, the diagonal matrix you get is just a string of zeros and ones. Okay, and so if the entries of the quantum permutation commute, you can write your after a change of basis, your quantum permutation is actually a direct sum of actual permutations. So that's why, and this is the sense why you don't care about the commutative case, because you're only going to see classical things. Okay, and so you define the quantum laws and grid set of quantum permutations to commute with AX. So that if you want to be, you might want to be a little careful here. I'm going to say this is standard usage, but you might say, well, it commutes with AX tensor ID for some D. But you can't just fix the degree, because if you've got a quantum permutation automorphisms P and Q of index D and E, then their co-product is a quantum automorphism of index DE. So the indices are going to grow on you. Well, they're going to become larger. You may not become fonder of them. And so there's a bit more. If you take a quantum isomorphism of index D going from X to Y, and you choose a density matrix, D by D, and we do our measurement. So we replace the IJ entry of the quantum permutation by its inner product with the density. So now you get a matrix whose entries are real. Okay, and because the projection sum to the identity, you discover that, well, because these are both positive semi-definite, the entries are not just real, they're non-negative. And because this is because this is effectively a measurement, because this sums to ID, the entries sum to 1. So you get a matrix which is relevant column stochastic. And it's, well, again, there's another exercise here. That W stochastic matrix commutes with the adjacency matrix. So a quantum permutation, after you measure it, gives rise to a fractional isomorphism. And so you can think of fractional isomorphisms as, in a certain sense, as being a special case or a reduced case of quantum permutations. Now, the consequence of this, if the graph is controllable, if the algebra generated by A and J is the full matrix algebra, then the only things that can be with A are scalar matrices, and so there's no non-trivial fractional isomorphism, and so there's no quantum automorphism. It's not non-trivial quantum automorphism. So for a controllable graph, instead of quantum automorphisms is trivial. It's just the identity operation or matrix. Okay, and it's a deep theorem, but it's true that almost all graphs on n vertices, proportionate graphs on n vertices, is controllable, goes to n, goes to 1 as n goes to infinity. And so you, well, equivalently, and you'll see that it's true that if you pick a graph at random, its quantum automorphism group will be trivial. but the way that's proved is first I say you pick a graph at random, it has no non-trivial equitable partitions, so it's in some sense the same proof. The advantage of controllable is you can actually test in polynomial time whether a matrix is controllable, but there's no test to say whether a matrix is random or not. But anyway, there's equivalence. So random graphs, most graphs don't have any interesting automorphisms. They don't have any interesting quantum automorphisms. So, well, now I'm coming to justify a remark I made at the start. One of the reasons we're interested in quantum automorphisms is that the commutant, we're interested in coherent algebras, is that the commutant of a set of the quantum automorphisms of what n by n is Schur closed. Okay, so if I read the word quantum, maybe I should make that permutation. Let me fix that. So, well, I did this before in the permutation case, and the same argument as I used then tells you there's enough to prove this when your set of quantum permutations is single to just one permutation. In the general case, just follows by taking intersections. Okay, so that's fine. And so we'll come to the proof. So we're looking at the ij block of M tensor I times our quantum permutation. Now, you may need to go off and think about this a little bit, but you'll see that that ij block can be written in this form as the sum M sub IR times P Rj. So this is a scalar and this is a projection. So this is the ij entry. So the ij entry, the product is equal to this. Now, our assumption that P and M tensor I commute gives us that this is equal to the ij block of this. And so you work out and you get this. Now, so if P commutes with M tensor I, then these two things are equal. And it only occurred to me while I was writing down these very notes. There's a bit more going on at P at first, because these are projections, and they're in the same. They come from a quantum permutation. They're in the same column, so they commute. The pairwise orthogonal. And so this is just a linear combination of pairwise orthogonal projections. So this is effectively a spectral decomposition. And these will be the eigenvalues, and these are the projections. Now, the crazy thing is, of course, the same is true for this. And these are the projections, and giving me the eigenspaces, and these are the eigenvalues. But these two matrices are equal. So they have the same eigenvalues. And I don't really know what that means at this point, but it's actually in some sense tied up with what we're trying to prove. So, but my point is that saying these two things are equal is saying something sort of structural. It's not just some fact that two sums turn out to be equal. Okay, so we have these two sums being equal, and so now I want to prove that we're get Schur closure. So I'm going to need to have a matrix M tensor I and a matrix N tensor I, and try and get some Schur closure out of that. So the first thing I just noticed that in that situation, well, I have the ij entry of N tensor I times Phi and the ij entry of M tensor I times Phi. Okay, and I'm taking a Schur, and so I'm noting that this product is equal to this, because these guys are projections and these are spectral decompositions, and so the product of the entries is we're just effectively multiplying the n. So this is the entry. This is so this is going to be M circle and M circle. Right. So there's my Schur product item. Okay. So this is equal to that. So, and as I said, so the right side here is equal to the ij block of this. Okay. Now, similarly, you can swap those and take transposers, and we get the, so I'm now dealing with, well, take transposers, I get this. Okay. But the point about this is because, oops, no way. Oh, you can't see it anyway. Because because this is equal to this, I can argue that the left-hand sides of these two equations are equal. So that implies that the right-hand sides are equal. And that then gives me exactly what I want, because this is giving me, this is M circle N. So the conclusion then follows that if, well, so the conclusion then is that if M circle N commutes with this. Okay, so we're closed under shared product. Okay, and since the commutator is automatically a matrix algebra, and since J is in here, we actually have a coherent algebra. Now, one other axiom for coherent algebras, which I've mentioned once or twice, is that we want it to be closed under, well, transpose or complex conjugation. It turns out not to matter, because if you close, because the standard basis is 0, 1, the complex conjugate of a, the conjugate transpose of a basis element is just a transpose. So the two terms are equivalent. In some cases, it's generally better to think of things as being invariant under transpose and complex conjugation as two separate operations. But for what we're doing here, it doesn't really matter. So I can say transpose close or star close. If I'm not working with over the reals, it's more natural to use star closure. But whether you use star closure or not, the canonical basis is closed on the transpose. It's a canonical basis consists of real matrices. So we need to show that the commutant of the the commutant of the quantum permutation is star closed, and I've sketched a proof there. So I don't think there's any need to go into the details of this. And so the conclusion then is that the commutant of a set of n by n quantum permutations is a coherent algebra. Now, actually, I think that will be. Now, yeah, actually, I just want to show you one more thing. The coherent algebras were first appeared in work by a set of coherent configurations appeared in work by Feit and Higman, classifying things they called generalized polygons, which I'm not going to go into right now. But this was motivated by some questions in the understanding of finite simple groups. Okay, and so they used coherent algebras. The second place they turn up is when people start trying to work out algorithms for graph isomorphisms. Okay. Now what have I done here? So the point is the automorphism group. Let's go back to dark color. So the automorphism graph consists of the permutations the commutant. If the permutation matrix gives you an automorphism, it's known as a commutes with the adjacency matrix. Now, and so this is an algebra, and so the bigger this algebra is, the more restrictions you have on the permutations. Now you stare at this for a little bit, and then you realize, well, it should be permanent intersection. This is redundant. Permanent J. Every permutation matrix commutes with J. It's trivial. And should be interpreting what I just wrote. This is terms in the commutator of the algebra generated by A and J. Because if you commute with A and you commute with J, you compute with any products of A's and J's and everything, any combination of products of A's and J's, so you commute with all this. And so, well, and it's not just that, it actually commutes with the covariant algebra. And so, well, this is the biggest algebra in sight. And so if you're working out the automorphism group of a graph, in a certain sense, you're going to have to work out what a large part of the structure of this covariant algebra. You may not do it explicitly, but that's what you're working with. And it's the size of this algebra that's going to govern what's going on. Now, as I remarked on several occasions, the algebra generated by these guys is often the full matrix algebra, and so this certainly contains that. So in most of the cases, everything collapses. But the point is that the covariant algebra is, in some sense, the biggest algebra around, which you know is closed, commutes all the permutations. So information about that can help you get information about the automorphism group. And I'll stop there.